Welcome to my talk about our paper, Fostering Engagement through a Latency-Optimized LLM-based Dialogue System for Multimodal ECA Responses, by myself, Konstantin Kühlum, Jonathan Ehret, Thorsten Kuhlen, and Andrea Bünsch. First, I would like to start with our research objectives, as our paper tackles three different ones, all connected to multimodal LLM-driven dialogue system for ECAs. In recent years, large language model, or LLMs for short, have become a very popular way of controlling embodied conversational agents, or ECAs for short. There already exists plenty of use cases, for example in education, medical applications, or scene-altering techniques. These new systems are rising through the recent developments in the field of LLM research and replace classical ways of controlling ECAs, which were, for example, through decision trees, through rule-based models, or through Wizard of Oz interfaces. Therefore, our first research objective is to build a holistic framework for multimodal ECAs by integrating existing technologies in a modular and developer-friendly system. Secondly, for a natural conversation, a low response latency by the conversation partner is required. There already exist ways of reducing the perceived latency by, for example, applying multimodal feedback during the response generation. But we instead would like to optimize the technical induced latency instead, by incorporating streaming optimizations especially tailored for multimodal ECAs. Lastly, we want to evaluate the interaction quality in terms of naturalness, perceived competence, and trust. We chose one of the classical conversation systems, the Wizard of Oz, for comparison, where a human controls the behavior of the ECA through an interface. Let us now start with our first research objective, building a holistic and use case independent LLM-driven framework. Here we see our main building blocks in a typical user ECA conversation. Of course, the user and the ECA. When the user now starts talking, their speech must be converted to text with a SCT. In our case, we used Google Cloud here. The recognized text alongside some metadata is sent to the decision making, which generates a response using an LLM, but also handles things like memory and response validation. We used GPT-4o here, as that was the newest LLM at the time. The decision-making also receives further information about the environment, for example, which location exists in the scene. We will see about that later. It is also possible that an event in the environment triggers our system, which we call then an environmental trigger. This might be, for example, when the user approaches the ECA. Lastly, the ECA also supplies some information about itself to the decision-making, for example about its identity or some character traits. When the response was generated by the LLM, it is oralized using a TTS. In our case, we used AWS Poly here. This audio is also used for generating the lip and face movement. The LLM also controls multimodal behavior, which in our case is divided into self-behavior and task execution. We will now take a closer look at how this is implemented. So, our system implements this multimodality by instructing the LLM to generate a JSON response, as you can also see in this picture here. Our system is generally capable of defining any field. Our implementation uses a spoken response, an attention target for gazing, which also allows for shared attention between the scene and the user, face emotions and gestures from a predefined set, and optionally a move target where the ECA should walk to, allowing it to navigate the scene autonomously. Let us now take a look at a very basic example from our use case. A VR user asks our LLM-driven agent for advice at a painting to answer their tasks.
The Oxbow is an intriguing painting by Thomas Cole, created in 1836. It captures a romantic landscape that uniquely represents the American wilderness. What would you like to know about it?
What is the name of the river? Is that a real river?
Yes, the river depicted in the Oxbow is a real one. It's the Connecticut River. Would you like to explore more about this painting or move on to another?
Did the artist have a special connection to the river? Did he know it?
Thomas Cole was indeed familiar with the Connecticut River region, as he's known for his profound appreciation.
As you may have noticed, the answers by the agents are really late, or in other words, there's a high response latency. To solve this issue, we will now take a look at streaming optimizations, our second research objective. For that, we first take a look at our system architecture again. Here we can see the critical path. First the SDT, then the LLM, and then the TTS. All of these components introduce some latency in the overall response latency. Let us also denote the transitions between these components with 1, 2, and 3 for later. Now we will first take a look how we can optimize the first transition here. We can improve the latency of the SDT component, the first transition, by streaming the input audio from the user in real time. The classical approach many use is to capture the audio and send it right after the user stops talking. And after a short while, the response from the SDT comes in. And the interval between these two steps is the critical latency of the SDT. And that is the latency we want to optimize. Instead, we can use streaming and send the audio while the user is talking. We can see that here now. As you see, the SDT system already has some internal state, meaning that when sending the last partial audio data, the response can come in much quicker since less audio data is left for transcription. This effect is even greater with longer input length. For the LLM, we can also make use of streaming features. As the LLM processes so-called tokens, we can work with earlier tokens in the response before the complete answer has been generated. Let us first take a look at the base case again. The LLM service generates a response, which is then sent to the TTS, and the audio is then played to the user. Instead, we can use partial text during generation. Our system does this, for example, sentence-wise. And as you see, the delay until the audio is first played at the user is reduced, and therefore the overall critical latency of the conversation is reduced. How that exactly looks, we will take a look at now in our demonstration here. We will only take a look at two cases, which we call here A and D, which is without any optimizations, and with both optimizations enabled. If you need more information here, please take a look at our paper to see how the other two scenarios are made up. Could you please tell me something about the painting here, the oxbow? What, for example, is the name of the river in it? Is that a real river?
The oxbow depicts the Connecticut River, which is indeed a real river in the United States. The painting showcases a dramatic contrast between the wild, untamed landscape on one side and the settled, cultivated land on the other, emphasizing the theme of nature versus civilization.
Could you please tell me something about the painting here, the oxbow? What, for example, is the name of the river in it? Is that a real river?
The oxbow depicts the Connecticut River, which is indeed a real river in the United States. The painting shows.
So, as you see in this example, streaming improved the response by 66%, and that would be even greater with higher input lengths. For the effect of input lengths, please also refer to our paper here. So far, we have created and optimized a holistic task-independent LLM-driven ECA dialog system. Now what is left to do for our third research objective is to evaluate the interaction quality by comparing it against a rigid Wizard of Oz. To do this, we conducted a user study in which the participants had to do a scavenger hunt for a virtual museum with the help of ECAs. The ECA was here controlled with a button-based Wizard of Oz interface, which had the same feature set as the LLM, with predefined presets tailored around the task. it also had a method built in for time measurement to later compare it against the LLM. Our first research question here was about the objective latency. We assumed the latency to be at least comparable between the Wizard of Oz and LLM after our optimizations. To just compare the decision making, both systems used TTS and lip sync. The result showed that the Wizard of Oz was about 6.5% faster. From these results, we conclude that the latency between the two systems is at least comparable, although the Wizard of Oz was slightly faster. Next, we investigated the perceived latency instead, and we assumed the Wizard of Oz to not be perceived as faster here, as we assumed that the more context-sensitive responses by the LLM would impact the perceived response latency positively. Our results, based on questionnaire data collected after every condition in VR, supports that, although not significant, suggests that even the opposite might have been the case, so the LLM might have been perceived as slightly faster here. In any case, we can conclude that the Wizard of Oz was not perceived as faster. Lastly, we investigated naturalness, perceived competence, and trust as quality metrics. We assumed that the LLM is perceived as better in these metrics, as it can generate more fitting responses than the Wizard of Oz, especially if participants behave differently than expected when designing the Wizard of Oz interface. We collected data by letting the participants directly compare a condition to the one before that, and by answering standardized questionnaires right after every condition. Our results are significant for all these subjective measures. Because of this, we can accept our hypothesis and say that the LLM was better in these terms, so naturalness, intelligence, and trust. This brings us to the end of the talk. So in our work, we built a holistic multimodal LLM-driven dialogue system and optimized the technical latency by introducing two streaming techniques. With that system, we then tested the interaction quality against a Wizard of Oz and can conclude that the LLM system was superior in all the measured quality metrics and was not perceived as slower in terms of response latency. With that, I would like to thank you for your attention.